Okay, we're going to look through some old tests over chapter 1 and 2. That's a good way to review for chapters 1 and 2. I'll just pick out problems that are relevant to those two chapters. The problems over chapter 1 are nearly always either find the Taylor polynomial of such and such a degree or find an error bound, and this one has both. If you want to find the Taylor polynomial degree 2, that's at a equals 0, that's f of 0 plus f prime at 0 times x plus f double prime at 0 over 2 times x squared. So it's just a question of finding f prime and f double prime at a equals 0. So you just take one derivative using the chain rule here, take another derivative using the quotient rule, plug in x equals 0, and you get log of cosine of 0 is 1, log of 1 is 0, sine of 0 is 0. It's minus 1, so it's 0 plus 0x minus 1 over 2x squared. Then the second part is a typical problem from section 1.2, find the bound on the error, and you need to know the Taylor remainder formula. It's for T2, the remainder formula is the third derivative of f at some point between x and a over 3 factorial times x minus a cubed. And now you need to calculate the third derivative. You need the first two derivatives for the part A, but you need the third derivative here. Use the quotient rule again, or chain rule. And you get a kind of complicated formula for the third derivative. Just plug in x equal 0.1, 3 factorial 6. But now this psi, you don't know where it is. All you know about it is between a equals 0 and x equals 0.1. But the numerator is largest at 0.1 and the denominator is smallest at 0.1, so just assume phi is 0.1. That'll make the numerator largest and the denominator smallest, and you get this answer here as a bound on the error. And here's another similar problem. This time the function happens to be a polynomial itself of degree 5, and you're supposed to find the Taylor polynomial of degree 3, which matches f at a equals 1. So it means it has the same value, same first derivative, same second and third derivative as the function at a equals 1. So you just have to calculate f prime, f double prime, f triple prime at 1. Those are polynomials, so it's easy to take the derivatives, plug in x equals 1, and those are the values you get. And there's the answer. Then error bound. Now this time it doesn't tell you what x is. So you need to know the Taylor error formula. It's Taylor polynomial degree n involves n plus first at some derivative at some known point over n plus 1 factorial times x minus a, n plus 1, a is 1. The fourth derivative is 120x, so the fourth derivative at psi is 120 psi over 4 factorial. So you don't know what, all you know about, well, you don't even know where x is. So you say, well, what's the worst case on x? Well, if x is between minus 0.5 and 1.5, x minus 1, the biggest it can be is 1.5 if x is minus 0.5, so it can be, so this is not symmetric around 1 here, this is unusual. X can be 0.5 above or 1.5 below, so the biggest this can be is 1.5 to the 5th power. That's supposed to be a 1 there. Now what do you use for the c here? Well, if all you know about x is between this and that, then that's all you know about this also, because it's somewhere between x and 1, so all you can say is this psi is somewhere between here and here, and the biggest it can be in absolute value then is 1.5. So the two separate issues here, what's the biggest this can be, what's the biggest that can be. If x is given, you just plug in x. If there's a range of x, you say, well, which value of x makes it largest, and then if you don't know what x is, so you can't plug in that value of x, you're trying to get a bound for all x in that interval, then all you can do is say that unknown point is somewhere in that interval also, because it's between x and 1. So you get 37.97, which is pretty darn large. Now this is section 2.2 problem. This is a quadratic formula. If b is positive and very large compared to AC, that means this is approximately the square root of b squared, which is absolute value of b. So you got minus b plus b. Those nearly cancel, so you've got a serious problem with round-off error. Remember in chapter 2 we said that the root of all serious round-off error problems is subtracting two nearly equal things. Well, that's exactly what we're doing here. The other root with the minus, you're not, because they're both minus b, but these are nearly canceling, so that's going to have a serious round-off error problem. Well, all you do is multiply and divide by the conjugate, that is minus b minus the square root, and the reason you do that is because you end up with b squared minus the quantity b squared minus 4ac, and the b squares cancel and you just get 4ac, so you basically just get rid of the problem. Now in the denominator you have minus b minus that, but that's not a problem because these are both negative. That b is positive, so the square root of b squared is b, so there's no problem here, and so this is more accurate numerically than that. Okay, here's an interesting problem from section 2.1. We have a 32-bit word on some fictional computer which has 22 bits for the mantissa and 9 bits for the exponent. Well, 22 bits for the mantissa answers the third part here, that the machine precision is approximately 2 to the minus 22, because 22 binary bits. Now the overflow and underflow, well, that has to do with the number of bits for the exponent. And even though this isn't exactly the way the exponent would be handled, but basically it's equivalent to having 1 bit to tell you whether the exponent is positive or negative, and then 8 bits for the absolute value of the exponent. Again, that's not quite the way it works, but it's equivalent. So basically you have an exponent which you can represent by up to 8 bits, which means essentially 256. So the smallest number can handle is 2 to the minus 256, and the largest would be 2 to the 256. So the underflow and overflow has to do with how many bits are available. The exponent, the precision, has to do with how many bits for the mantissa. This problem is almost the same as the last one we looked at. This one is only slightly different in that, let's see, we got a polynomial of degree 3 that approximates this polynomial of degree 4 at a equals 1. If we took the Taylor polynomial of degree 4, it would be exactly equal to f everywhere, of course, because the fifth derivative would be identically 0 everywhere. But it's not quite matching, so get a reasonable bound on the error between minus 1 and 3. Well, you just need to remember the Taylor error bound. It's n plus first derivative, where n is 3, at some unknown point over n plus 1 factorial times x minus a to the n plus 1. That you need to remember. A is 1, n is 3. What is the fourth derivative? Well, it's a fourth degree polynomial, so the fourth derivative happens to be a constant, which is nice because now you don't have to worry about where that unknown point psi is. Doesn't matter. It's 48 regardless. And the biggest x minus 1 can be is 2, because that's as far as it gets from 1. So you assume x minus 1 is 2, and fourth derivative is constant 48, so there's your error, maximum error bound. And this problem is almost identical to the one we just did in the last test. Okay, this problem is a little bit different in that it doesn't ask for the Taylor polynomial of a degree 3 or 4. It does for general n, which for some problems will be very difficult because the nth derivative is pretty hard to say for general n, but for e to the 2x is pretty easy. Every time you take a derivative you get a power of 2, so after n derivatives you have 2 to the n e to the 2x. And at x equals 0, at a equals 0, the e to the 2a is 0, so it's just 2 to the n. So 2, 4, 8, up through 2 to the n, that's f of 0 is 1, f prime is 0 is 2, f double prime is 4, f triple prime is 8, so forth. And then the second part is typical again, except that it's for general n now, so the get a bound on the error at x equals 3. So x minus a is just 3, so that part's easy. N plus first derivative would be 2 to the n plus 1 times e to the 2 unknown point. And that unknown point is somewhere between a equals 0 and x equals 3. So the biggest, since e to the 2x is an increasing function, the biggest that can be is e to the 2 times 3, or e to the 6. And so here's your bound for general n. 2 to the n plus 1 is the n plus first derivative. Comes from the n plus first derivatives. This x is 3 is the, what's the value of x. So there's your bound, and doesn't give a specific value of n, but you can see that the bigger n gets, the smaller the error is, even though 6 to the n plus 1 grows with n factorial, n plus 1 factorial grows a lot faster. So if n is 100, if you take 100 terms, this is almost 0, because 101 factorial is so much bigger than 6 to the 101. So you're going to get small error when n is large, although they didn't actually ask that. And here's another 2.2 problem. When x is nearly 0, this is nearly 2 minus 2 in the numerator, so you're going to have serious round-off error problems. So you multiply by the conjugate, and the reason that works is the cross terms disappear and you get 4 plus x minus 4. And if you evaluated that, you still have the problem, because 4 plus x is nearly equal to 4, but you just cancel the 4's with the eraser here, and you got x, and the x, well, you can cancel that x there, although that's not important. And in the denominator, this is approximately 2 plus 2, so there's no problem. If you actually calculate this on the computer, this will give you good results. When x is real small, this will not. Here's a section 2.1 problem. We have two fictional computers. They both have the 128-bit words. One of them has 21 bits for the exponent, the other only has 13, but it has fewer bits for the mantissa. So which computer can handle larger numbers? That would be the computer A that has more bits for the exponent. And approximately what is the overflow limit? Well, it has 21 bits to store the exponent, and even though this isn't exactly the way the numbers are stored, it's the overflow limit. You'll get it essentially correct if you just pretend like one of those 21 bits is a sign bit for the exponent. It tells you whether the exponent is positive or negative. So you basically got 20 bits for the absolute value of the exponent. So how big can the exponent be? Well, 2 to the 20th power, which is about 1,000,000. And some students said, well, the 1,000,000 is the overflow limit. No, 2 to the 1,000,000 power. 1,000,000 would be an awfully small overflow limit. It's 2 to the 1,000,000 power, which is about 10 to the 315,000, which is a really huge number. That means 1 followed by 315,000 zeros, so you're not going to need numbers bigger than that. That's a very large overflow limit. Now, which has higher accuracy? That would be B, because it has more bits in the mantissa, and its accuracy is 2 to the minus 1/14, which is approximately 10 to the minus 35. So how many decimal digits does it have? About 35 then. So that's pretty accurate. Okay, here's a problem where they talk about the Taylor polynomial of a general degree n. That makes it a little harder, but this function, it's easy to take the n plus first derivative, nth derivative. It doesn't ask for the Taylor polynomial itself, just for bound on the error for x from minus 2 to 2. So if x is the interval minus 2 to 2 and we're expanding around a equals 0, get a bound on the error. Well, you just need to know the Taylor remainder formula that for Tn, it's going to be the n plus first derivative is unknown point over n plus 1 factorial times x n plus 1. Well, x minus 0, a is 0. To n plus 1. Well, the biggest that x minus a can be is 2, so you just plug in x equal to 2, and then the n plus first derivative of e to the x over 2 would be 1/2 to the n plus 1 times e to the x over 2, because every time you take a derivative you get a factor of 1/2, so after n plus first derivative you're going to have a factor of 1/2 n plus 1 times, then you still have the e to the c over 2. And now, what is c? Well, it's somewhere between a and x is between minus 2 and 2. So the biggest c can be, c is also has to be between minus 2 and 2, because it's closer to a equals 0 than x is. So you assume worst case c is 2, and that gives you e to the 1. And then the 1/2 to the n plus 1 and the 2 to the n plus 1 just cancel. So you get e to the 1 over n plus 1 factorial. And then they ask, so how many terms do you need so that the error is less than 10 to the minus 10th? Well, you kind of have to do this trial and error because the n plus 1 factorial, you just have to try larger and larger values of n until this is less than 10 to the minus 10, and 13 seems to work. So if you write the Taylor polynomial degree 13 that approximates that at 0, you're guaranteed an error of less than 10 to the minus 10 in the whole interval minus 2 to 2. Of course, outside that interval, it could be a lot more than that. Well, this is another section 2.1 problem, very similar to the one we just did. This computer has 17 bits for the exponent, 110 bits for the mantissa, so the machine precision is about 2 to the minus 110, which is approximately 10 to the minus 34. The overflow limit, again, 17 bits. You can pretend like 1 bit is used up for the sign, so you basically have 16 bits for the exponent. 2 to the 16th is about 65,000. That's not the overflow limit. That's the biggest. E can be as big as 65,000. That means numbers can be up to 2 to the 65,000 or 10 to the 19,000, which is really huge.